recording. So, hi everyone, welcome to MacX Build, building an end-to-end machine learning project. Before we start today's event, I wish to acknowledge the traditional owners of the land on which we are gathered today. So I'm Sai, I am the current events director, Monash Association of Coding, Mac for short. Thank you for coming today. So I'd like to talk about who we are. We're a tech club that focuses on providing valuable technical skills and industry relevant experiences to students. Our goal is to foster the tech culture on Monash and provide a collaborative setting for students to learn from one another and build upon the skills they need for a career in tech while making friends along the way. So don't forget to check us out on social media. I said that before, and I'll be sending it off to Sid now to begin today's session. Sid, take it away.
Thanks, Sai. Hello, everyone. My name is Sid. I am Vice President this year at Mac. I'm studying Bachelor of Computer Science, specializing in data science. And today we'll look at how to build sort of a fully fledged machine learning project. Let me share my screen. So Sai will send a link in the chat for a notebook that we're going to follow for the rest of this workshop. But let's start by talking a little bit about the ML lifecycle. So actually, before that, I want to also set some expectations for this workshop. This is going to be a 2-hour workshop, and we will do pretty much everything until actually productionizing our model. So because this is a fairly lengthy workshop, I won't delve too deep into actual machine learning theory because it's very easy to get lost in that. This will sort of give you an idea of all the steps that go into building a machine learning project. But if you want to learn more about actually productionizing it, Sai will be doing a workshop about that sometime later this semester. So keep an eye out. But the other thing is we will also not go too deep into the Python programming language because the sort of expectation is that you have basic understanding of Python, data structures, control flow, and all of that. Having said that, let's start with the machine learning lifecycle. So when you get a new machine learning problem, the first thing we do is sort of frame the problem in a machine learning context. So the problem we have today is that we have a data set of house prices, median house prices in California. And the model we are trying to build is a prediction model that will predict house prices given some features. So machine learning models can sort of be on a high level divided into 2 categories, supervised and unsupervised. So supervised machine learning algorithms are algorithms where you have both features and labels. Labels are the items that you're actually trying to predict, which in our case is the median house value. And labels are the sort of predictors that you base your prediction of the label on. So if you have both features and labels, it is a supervised machine learning problem. But if you only have features and no labels to go off on, this is an unsupervised machine learning problem. So in our case, it is a supervised machine learning problem. Now, within supervised machine learning problem, you have some more subcategories. You have regression problems, which is where you're trying to predict a value, let's say a numerical value, which is the case in our situation. You also have classification models where you're trying to predict what class a data point belongs to. You can have sort of binary classification problems where you predict either this or that, maybe sick or not sick, male or female. You also have multi-class classification models. A good example of multi-class classification could be like image classification problems, where you could theoretically have infinite classes. Yeah, so um, ours is a regression problem um, because we're trying to predict a value. And a lot of people, when they hear the word regression, they associate it with strictly linear regression. Linear regression is sort of like the most basic regression algorithm, but regression in itself is not just an algorithm, it's sort of a problem type. Um, Regression problems can be solved with many different algorithms, and linear regression is just one of them. Uh, Having said that, we will start our model with linear regression, and then we will sort of go into more complex models like decision tree regression models, random forest regression models, and so on and so forth. All right. So the first thing we will do is set up our machine learning environment. Um, let's see. Okay. Okay. So I'm guessing everyone has Python installed. So the first thing we need to check is if we have pip installed. Pip is Python's default package manager. We are going to use pip to install all the libraries that we need for this project. So I have a folder here that I've created. So I'm going to open a terminal here. You can, if you're on Windows, you can open PowerShell or command prompt. And then you can check whether or not you have pip installed by writing Python 3 m pip version. And then it should give you a version if pip is installed. It's also a good idea to update pip before we do anything else. Actually, uh, yeah, so let's do that. Okay, so we already have pip installed. So I'm going to give everyone some time to make sure you have pip installed because that is a requirement for what we're going to do next. But yeah, while everyone is doing that, I want to talk a little bit about virtual environments. So when you install packages, when you install Python packages, without creating a virtual environment, they're sort of installed into your root folder, and they can be accessed from anywhere. The reason we want to create isolated environments is, for example, to avoid version conflicts. So let me think of a situation. So let's say the latest, so one of the libraries that we are going to use is NumPy and pandas. So let's say the latest version of pandas right now is pandas 15, and the latest version of NumPy is NumPy 11. And pandas actually depends on NumPy because it uses NumPy to do some of its operations. So let's say you're working on a project where you need, for some reason, instead of NumPy 11, you need NumPy version 9. So you install NumPy version 9, but pandas needs NumPy version 11 to run. So when you actually then try to run pandas, it will say that the required version of NumPy is not installed. So those are the situations that we want to try and avoid. So what creating an isolated environment will do is you can install specific versions of packages that will just be accessible from this project. That way, if you need a specific version of a library or a package, you can do that without having conflicts. All right. So the next thing I'm going to do is, so I'm currently in this folder. I'm going to create a new folder here called MacML. And if you haven't, you don't have to use terminal to do this. You can create a new folder. So the way you create a new folder in terminal is with the mkdir command. So I have that, and then I'm going to go into that folder using the cd command, which means change directory. So I'm going into MacML, and you can check which directory you are right now with this command pwd. It means print working directory, and it tells me that I'm currently in MacML. The next thing I want to do is create a virtual environment within this MacML directory. So I can do that using this command, python3 -m venv. And then this env at the end is just a name that we have given this environment. So you can put any name you want. It can be the name of the project, but I'm just going to use env for now. So we'll just wait a bit for the environment to set up. And then what we have to do is activate that environment. So to activate this environment, if you're on Mac OS or Linux, what you can write is source and then env/bin/activate. Essentially, what we are doing is we go into this folder, you'll see that a new folder was created, which contains our virtual environment files. This is where all of our packages for this project are going to be installed. So if you go into that and go into bin, and then you see this activate executable file, that's what will run when I run this command. If you're on Windows, the command is this. Windows uses backslash, so it will be ./env/scripts/activate. If you have any trouble with that, let me know. All right, so it tells me that I have activated the env environment with this signal here. So now that I am in my environment, I can install the scripts that I need, so the libraries that I need. And the way you deactivate an environment is just by writing deactivate into the terminal. So we need, for this project, we're going to use Jupyter, which is a notebook environment, which is where we will write our code. We'll use matplotlib, which is a plotting library. We'll use NumPy and pandas. They make it very easy to handle tabular data. SciPy and scikit-learn are two machine learning libraries that we're going to use. Scikit-learn is probably the most used machine learning library in Python. Even some more advanced machine or specialized machine learning libraries like Keras, TensorFlow, or PyTorch use scikit-learn under the hood to do some of the operations. So I'm just going to copy this command from here and then paste it in my terminal. This command should be the same for Windows, Mac, and Linux. And I press enter. This is going to take a while, maybe 2 or 3 minutes. Scikit-learn is a pretty big library, so that might take a while to install. While that's being installed, if anyone uses Conda as a package manager, you could also use Conda for this. You don't have to use pip. In fact, I personally use Conda, but Conda takes a little longer to set up, so that's why I'm using pip today. Let's wait for that. Okay, while that's going on, let's have a look at our data set today. So for features, we have latitude, longitude, median house age, total rooms, total bedrooms, population, household, median income, median house value, and ocean proximity. So every row in this database, in this data frame, is a district in California. And total rooms is basically the total number of rooms in that whole district, not just one house. Same for total bedroom. Population is the population of the district. Yeah, I'm not going to look at the data too much from this file. What's up here? Is it stuck? It's still working. Okay, let's wait for that. So what I've gone ahead and done is this data set is actually available on Kaggle if you want to download from there. But I have uploaded it to GitHub, and then I've put the link in this notebook here. So we're going to directly download that data set from this URL, and I'm going to explain in a bit why that is a good idea. Okay, so looks like that's weird. It says pip there's an upgrade for pip available, but we just tried upgrading like a few seconds ago. Maybe there was a release while I was talking. Interesting. All right, so now that all our packages are installed, I am going to open up the environment where we're going to actually write and execute our code. It's Jupyter Notebook. So if you write Jupyter space notebook and press enter, it should take a few seconds, and then it'll spin up a local server on your machine, and then you can click one of these links to open up the environment. All right. So right now we are in the file that I created. So what I'm going to do is create a new notebook, and because we're using Python, I'll click Python here. Let's see. Okay, well, that's going on. All right. So the first thing we're going to do is download our data set from the link that we talked about before. So to do that, we need a few libraries. Actually, before I do that, let's talk about Jupyter a little bit. So if you haven't used Jupyter before, it is a notebook environment with cells. So in each cell, you can write and execute code that's separately. But what's important to understand here is that even though you can execute the code separately, they are sharing the same kernel and memory space. So let's say, for example, if I do x equals to 5, and the way you can run a cell is you can click run here, or you can click control plus enter, or command plus enter probably for Mac. And then you can add, let me add a new cell. And if I just print out X here, you'll see that it's sharing the same memory. So they are not, the cells are not isolated, all right? So going back to downloading the data, so we will need to import some libraries. We'll need OS. We will need dar file to extract our zip file. And we will need URL lib to download the file from our URL. Cool. The next thing I'm going to do is get the address or get the path of the directory that we are in right now, because we need that to save the file later. So what I'm going to do is create a new variable called pwd, which stands for present working directory. And you can use the get cwd command function from OS to get the present working directory. So let me check if that worked correctly. So I can then print pwd. Yep, it tells me the correct path. What I'm going to do then is save the URL for our data file. And the URL should be in the notebook. So you can just copy it off there. I'm just going to copy that and then paste it here. Oops. And then we also need a path to where we are going to locally save this file. I'm just going to call that housing path. And what I'm going to do now is I'll create a path for this, and I'll write the code first, and then I'm going to explain why I'm doing that. So within our current directory, I'll create a new folder called datasets, because sometimes if you're in a big project, you might have multiple datasets and you don't want to store the datasets in your main project directory. So I'll create a folder called datasets. And within that folder, if I have multiple different datas, I'll create a folder called housing within that folder called datasets. So the reason instead of just storing this path as a string, I could have just added /datasets /housing in our present working directory path. But the reason I'm not doing that is, let's say when you productionize this model, it could run on many different operating systems. Maybe it's running on Linux server. If someone downloads the model, maybe it's running on their local Mac OS. And every operating system defines these paths differently. Linux and Mac uses /, Windows uses \. So we don't have like cross OS compatibility there. So, but doing this gives you cross OS compatibility. And sort of like OS agnostic, you can use it in any OS. So I'm going to print that out to see if that's actually done correctly. Also, I'm not able to see the chat. So if anyone puts a question in this chat, Sai, if you can please help me out. Yeah, so that looks like it's correct. So within the directory I created, there will be another directory called datasets, and within that housing. Okay, that looks about right. And then what I'm going to do next is I'll write a function to download and extract our dataset. The reason I'm going to do that is if you imagine if you are querying data from a database that changes every day when new data comes in, you want a function that you can just put in a script and run every time in like regular intervals to get the data. So that's what we're going to do. So I'll write a function called download data. And this function will take in two arguments, housing URL, which is the URL where the data is stored, so which is this. And then the other argument will be housing path, which is where the data file will be stored, which is this. So now that we have both of those, the first thing we have to do is actually create this housing path directory. So I'm going to use the make dir function from OS to do that. OS make dirs housing path. And I'm going to do exist OK equals to true. What that means is that if it doesn't exist, then don't make another one. And I'll create another path to store our our zip file. It's in DGZ format, if you can see on the URL here. So what I'll do is I'll do os.path.join. our housing path with the file name. So I'm just going to save that as housing.dgz. So that's, and we can try and run this in a different cell. Actually, so I should probably say this. So you don't have to click insert cell below every time. You can click B on your keyboard to go to a new cell, but you have to get out of the edit mode first. So right now I'm in the edit mode in a cell. You can go to command mode by pressing the escape key on your keyboard. So now that it's gone to command mode, I can add a new cell below it using B or a new cell above it using A. And I can delete a cell using X. Cool. So let's see if that does what we think it should do. Oops. Yeah, that looks about right. I'll delete that. All right. So now I'm going to download the file, and I'm going to use the URL lib library and URL lib.request URL retrieve housing URL, and then save it into DGZ. Right. So what we have to do next is extract this zip file, and we can do that using, actually we have to open the file first. We do housing DGZ is equals to dar file dot open DGZ path, which is where the file is. Oops. And then we do housing dot DGZ dot extract all, and that is going to be housing path, which is the path we created before. And then at the end, we also want to close the file that we opened here just to free up that memory. Oh, so that's our function, which will download the file as a zip file. Then it will open the zip file. It will extract the zip file into housing path and give us the data. So let's see if that works. So I'm going to do download download data. And we don't need to pass any arguments into it because by default, it takes these two arguments. So I'm just going to do Control Enter to run that, and it will take a while. Oops, did I? Oh, I didn't run this cell, so it doesn't know that this function exists yet. So I'll run this cell first. We have this function, and then I'll run this, and let's check if we have the data in the correct directory. That's that. Yeah, so data sets, housing, CSV. Probably should have deleted this file, but that's okay for now. So what we're going to do next is read the file that we just downloaded, and we can do that. So to read our file, we need to import the pandas library. So what we're going to do is import pandas as, and then I'm just going to give it an alias. This is the convention to use pandas. Most people just use it as PD. And then I'm going to define another function that will load our data into a data frame. So we'll do load housing data. We'll take the path where we save the file, housing path, and by default, it's just going to take this path here. So what we want to do is we have to create another path called CSV path, which is going to be os.path.join our housing path, and then we just concatenate the file name at the end, housing.csv. That should give us the path for the CSV. Housing just gives us up until this directory here, and then you add housing.csv at the end to get the full path to the file. And then we're just going to load the file, load the CSV file using the pandas read CSV function. So we're using pd.read underscore CSV path. Oh, let's define that. Interesting. Why is that taking so long to run? Okay. All right. So let's now use this function to load our CSV file into this data frame called housing. So I'll do housing equals to load housing data. All right. So we should have the data in this variable here, housing. So the next thing we're going to do is, so what we'll start with is exploring this data a little bit and see if we can find any quirks about the data. So the way you can, we saw here that the actual data is very big. So we're not going to print the whole data. Maybe we'll just print the first few lines. And the way you can do that using pandas is you can do housing.head. And then by default, it prints the first 5 rows. You can do 10 instead, or maybe 3 instead to print however many rows from the top you want. There's also a function called tail, which prints rows from the end. So you can print 5, 10, or 15 rows from the end if you want. But this works for us. So housing.head, run that, and we have the first few columns. All right, so each row here represents a district. How many attributes are there? So attributes essentially are columns. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 attributes. Okay. So the other thing is some of these attributes are features, but this attribute right here, the one that we're trying to predict, is the label. Okay, so the next thing I'm going to do is learn a little bit more about these attributes, maybe things like what sort of data type are these columns? Maybe are there any missing values in these columns? So the way you can do that is name of the data frame dot info. So when you run that, it tells you the names of all the columns. It also tells you how many non-null values there are, which means like non-empty values there are. Most of them seem to be the same except for total bedrooms here. That means there are about 200 something null values in total bedrooms. And we'll probably have to fix that at some point. Most of these are numeric data types. So float 64 just means decimal numbers. And then this object here, which is this column, it looks like it's a string. So you can see like for the top 5 rows, the value sort of repeats, which probably tells us that this is some kind of like categorical variable. And we can check how many different categories there are in this column. So the way we can do that is housing, and then we select which column we want to look at. So ocean underscore proximity. And then we want to do value underscore counts. So that'll give us how many different categories there are in ocean proximity and how many instances of each category there are. So if I run that, it tells me that most of the districts are less than 1 hour from the ocean, some inland, very few on island. One good thing is that we only have 5 categories. So this is a bit premature, but at some point we will have to change these categories to numeric categories because machine learning algorithms are generally not good at uh, analyzing categorical variables. So we'll encode these into numeric. And it's good that there's only 5. So we don't need a lot of extra variables. Okay. The other thing we could do is sort of create a visualization for this to see the distribution here. So you can create a histogram. The way you can do that, so I'll just copy this part and then do dot plot. What we are using here is the pandas default plotting function, but it actually uses matplotlib under the hood. So actually, do we have to import matplotlib here? Probably not. Let's try. We can do kind equals to, let's do like bar charts. So kind equals to bar. Run that. Okay. So we have vertical bar chart, but horizontal bar charts are almost always better to understand. So you can just add a H here at the end of this bar, which just means horizontal bar, and then run that again, and that'll give you horizontal. Yeah, so pretty much no new information. We already knew that most of it belonged to this category here, almost none in Ireland. Okay, so the next thing we'll look at is sort of some summary statistics of the numerical variables here. This is just something that you do in data science projects. We're not going to spend too much time on it, but just for the sake of it, we'll do it. So we'll do housing.describe. So this gives you descriptive statistics, housing.describe, and run that. And then you see it gives you some descriptive statistics like count, mean, standard deviation, minimum, the first quartile, the second quartile, and the third quartile. If you don't know what quartile is, it means that 25% of the data is less than this value, 50% is less than this value, and 75% is less than this value. Cool. Not a lot, not too much interesting things here. Okay, this is probably interesting. So we can see that the minimum median income is 0.5 and the maximum median income is 15. And that probably tells you that this is not in dollars. It has been scaled in some way. My guess would be it has been just like divided by 100,000. So this is like 50,000 and this is 150,000. But that's just a guess. But yeah, the important thing is that it has been scaled. Yeah, so another quick way to sort of get a feel of the data is to generate histogram for all the numeric variables. And for this one, we are going to use matplotlib. So I'm going to import matplotlib, which is one of the libraries we installed before. So matplotlib.pyplot, which is the class that we're going to use. And I'm just going to give it an alias called plt. This is again also a convention, and it's always good to use conventions because anyone who's reading your code will probably expect these conditions. And there's a saying that code is actually read more than it is executed. So yeah, so just makes it easier for anyone who's going to see your code in the future. The other thing I'll probably have to do is this thing called matplotlib inline. And what that does is if you have used matplotlib in Python before, essentially if I don't put that in, it will use it'll create another GUI. So it'll just open our plots in a new window. But instead of doing that, we just want to output our plots within, sorry, actually it should say inline, output our plots just under this cell within Jupyter Notebook. So what this does, it tells Matplotlib to just use Jupyter to present the graphics. So what I'm going to do is I'll create a histogram for all the variables. And this is how you can do that. I'll just add some bins in. We can change this later. And then I'll give it a size because there's a lot of variables. And by default, it might just give you a very small plot. So I'll add a size here to make the plot bigger. All right, and at the end, you just have to do plt.show to get the actual plot. So I'll run that. This might take a while. Okay, so we have a histogram of all the numeric variables. But let's see what's interesting. We can see that median income is gapped between 0 and 14. The other interesting thing is that median house value is probably also capped at 500. That's why you see this very big spike at 500, which means that basically they didn't include any, either they didn't include any districts that had median house value over 500,000, or they just rounded it all down to 500,000. Either way, this is sort of problematic because this is our label. So we don't want this kind of bias in the label. We will probably fix it at some point. The other noticeable thing is that all of the variables are in very different scales. So this median house value is in the hundreds of thousands. This is scaled to fit between 0 and 15. This is in the thousands. This is in the tens of thousands. This is in the tens. So yeah, a lot of very different scales. And also some of these variables are really tail heavy. So they're right skewed, which is also probably not good. The reason is that a lot of machine learning models have a tough time with these heavy-tailed features. So we might also standardize this at some point. Okay. The next thing I might do is what I'll do is this. I'm going to bin the median income a little bit more just to make this distribution a little bit easier to see because there's not much after like 8 here. So I'm just going to copy a code and I'm probably going to do that a lot just because we have to fit this workshop into 2 hours. So this code should be in the notebook as well. Let's see, do I have that open? Yep. Okay. So I'm going to create some bins. And it will sort of become clear why I'm creating these 1, 2, 3, 4, 5 bins here. Especially because there are actually values over 6. But yeah, I'll explain that in a bit. And then I'm just going to do value.counts again. So I'm creating a new variable, new column called income cat. And then I'm just going to bin these values. So the labels are going to be between 1 to 5. So high means high income, 1 means low income. And let's run that. Okay, so what I've forgotten to do is it says NP is not defined, and I've used np.env here, which is So what I need to do is import the NumPy library. So I can do that using import NumPy as NP, which is again an alias. So let's run that now. Okay, so let's visualize this again. Let's take this, let's put it here, and then do hist again. Okay, that doesn't look right. I guess what this is doing, it's because the hist function bins, but because I've already created bins, it's sort of like trying to bin my bins. So I'm just going to take this out because I don't need to bin in again. Yeah, okay, so that does it. So what can we see from this plot? So most of the districts are in the middle income range, few in the high income, and few in the low income, which is realistic. All right, so what we'll do next is we'll do some more data exploration and like data visualization. But before we do that, what I'm going to do is create a test set and a training set. So I'm going to keep some portion, preserve some portion of our data set to test our machine learning model later. And the reason is that sort of like the goal of a good machine learning model is to generalize well from the training data to, let's say, like any unseen data that you give to it. And if it generalizes well, it will make good predictions on data that it hasn't seen. Um, the reason we preserve a portion of our training of our whole data set is to avoid this phenomenon called overfitting. So what overfitting is, overfitting happens when your machine learning model sort of picks up small details and noise in your training data, sort of to the extent that it negatively affects your performance on any new data. So it picks up small discrepancies in your training data that's actually noise, and it thinks they're a pattern. So when it then tries to generalize its knowledge on unseen data, it tries to predict following those like noise, but which it's not supposed to do. Yeah. So the opposite of overfitting is underfitting, which is when your model can neither learn the training data or generalize to any new data. So that's why we sort of preserve a portion of our data set to test our model later to see whether it overfits or underfits. Okay, so I'm going to copy some code again, and then I'll explain what I'm doing. So okay, so let's copy this part here. Yeah. So what I'm doing here is from the sklearn model selection class, I'm importing training test split. So the training test split function divides our dataset into two parts. And generally, we have about 20% or like 30 to 33% of our data set as test data, and the rest of the 80 or 70% of the data set as the data, the training data that will actually feed to our model. And I've added a random state here. So what that does, it lets you recreate this exact data set again, because test training split uses sort of like random number generation to get the training split. And because we might run this model, we might generate this data again. So I'm just adding a random state so that it's recreatable. Okay, so when we run this model, we will get a training set and a test set. So that might take a little bit. Okay, so what train test split will do is it will basically split your data horizontally into a training set and test set. And then the training set is the data that we actually pass into the model. And the model only trains on the training set. We will then later use the test set to test the accuracy of our model. And we will actually create another set called the validation set down the line, but we'll talk about that when we get to it. So the other thing we want to check is if our test set and training set is sort of representative of our original data. So let's imagine median house income is a significant median income is a significant predictor of what the median house value in a district could be. So when we are creating our test and training set, if by chance, like randomly, we create a test set which only has very high population, very high income districts, our machine learning model is going to start thinking that this universe only has high income earners. And then it will sort of, when it then gets new data that is low income, it won't know how to predict the house value for a low income district. So what we want to do is check whether these sets are representative. So we created this income cat category, right? So we can just run this histogram again to see if that still applies, like if the histogram still looks the same. So we can do train set dot hist. Oh, okay, no. So we want to do train set dot income cat. That's the only histogram we want to create. Yeah, so this looks pretty much the same as this one. We can also check the test set. That also looks pretty good. Although the issue here is that this train test split function randomly selects rows to put into our test set and training set. And because our data set is pretty large in this case, the training and test sets are sort of representative, but it might not always be the case. So what we'll do is we'll use a different function that's available from sklearn that uses something called a stratified split. So we'll look at that. Where is that? Okay. Yeah, so what stratified split essentially does is it splits your data set into homogeneous subgroups. So in our case, we want to split our data set based on the income category, and then we want to pick the right number of instances from each category to make sure that they were the same as our original data set. I'm just going to copy this code from here. Import that function, and you might see that like instead of importing the whole sklearn library at once, I'm importing functions one by one, and this is something that machine learning practitioners do quite a while, often when they're using sklearn, because sklearn is a pretty big library. So we're just only importing functions that we need. And then I'll just copy this code here. And then I'll explain what it's doing. So we imported this class called stratified shuffle split. And then what I'm doing is I'm instantiating that class. And I'm saying do one round of split. The test size will be 20% and just use a random state there. And then I'm storing my training set, and I'm just calling that strat train set, short for stratified training set, and strat test set. So let's run that. And then what I'm gonna do is I'm probably gonna skip doing the histograms again, just in conscious of time. Okay, so going back to why we binned our income category into six bins, because you can see here that most of the medium income is clustered between sort of like 1.5 to 6, but some do go far beyond 6. But for our stratified split, it's important that we have sufficient number of instances in each of our strats or each of our bins. And because if we make more bins here, each of these bins will have a really small number of instances. And what that does, it sort of overestimates the importance of these bins here, which it shouldn't do because most of the data set is here. And so the conclusion there is that we should not have too many strats. And also each strat should be sufficiently large so that their importance is not overestimated. All right, so we have our training set and test set that we are going to use for the rest of the project. So what I might do next is do some more visualizations. But before I do that, I'm going to create a copy of our training set. And the other thing you'll notice is that I will not touch this test set anymore until the end of the project when we have already selected a model and we are ready for testing that model. The reason is that when I'm doing this data visualization in the next step, and also when we do some more feature engineering down the line, the human brain is very good at like pattern detection. So I might subconsciously identify patterns in the test set if I hadn't separated it. And what that might do is it might make me inclined to choose certain models that might perform well for the data set if I see the training set. So I want to avoid subconsciously doing that. So I'm not just not going to look at the test set until the end. So from here on onwards, we will just look at the training set. So I'll just make a copy of the training set just so we don't mess it up when we are making our visualizations. And one thing here to note is that I'm using the copy function here because if you don't use that, let's say if I just do this, it won't create a new separate copy of this data set in like a different memory location. What it'll do is just create a variable that just refers to this. So what then ends up happening is if I change this, this will also change. So that's why we use copy. All right. So because we have geographical data with like latitudes and longitudes, it might be good to create a scatter plot to see how data is spread out. So I'll do housing.viz .plot. I'm using Pandas's default plot function. I could have used matplotlib, but this does the job. So kind equals to scatter. On the X, we want longitude. On Y, we want latitude. And then let's add a figure size. 15. And don't worry too much about the syntax here. You can come back to this code later and sort of figure out the syntax, but just pay more attention to the steps we're doing and sort of the reasoning behind those steps. All right. Okay, so if you haven't seen a map of California before, this is pretty much what it would look like. It has the ocean here, and it's sort of like a long strait. It's hard to see where the points overlap. So what I'm going to do is make the points sort of transparent so that we can see where the points overlap. So the way you can do that, you can use the alpha property. Alpha is basically your transparency. So I want to make this like maybe 25%. Should be good. Okay, so now we can see where most of the data is clustered. The other thing, and I might add another attribute here. What I'll do is I'll add the population here to see which areas are sort of like more densely populated. And I'll make the points vary their size based on the population. So what I'll do is I'll add another variable here called S, which stands for size. I'll do housing viz pop. Actually, why did I population and comma. Okay, that magnifies the dot a lot because I think the population is these are very big. So what I might do is I will just divide this by 100 to make it easier to see. Okay, that's pretty good. And then what I'm going to do next is sort of vary the colors of this plot based on the median house price. So we can see where the high house price districts are located. So you can do that by doing C equals to the name of the variable that we want to use. So we can do C equals to median house value. Oops. And then close quotations, comma, run that. Okay, that makes it black and white. So we need a color scheme. What I'm gonna do is I'm going to use the jet color scheme here, which is like a diverging color scheme. You don't have to worry too much about this. The code is going to be, whoops, I think I'm in insert mode. So I'm gonna use cmap equals to plt dot get cmap. Cmap means color map. Jet. That should be pretty good. Yeah, okay. So red is high house price. Purple is low house price. So what can we notice in this image? So as I was saying, this is sort of the Bay Area, and you can see that the high house price districts are located near the ocean, near the bay. So location is pretty important. The other thing that might stand out is population is also important, like the density. So if you see the big dots are more bluish, all of the red dots, like the smaller dots, if you see in the same location, all of the bigger dots are bluish. And the smaller the dots are, the more red they are, which also tells us that the house price is also related to um, the density of population. So, which means that like less densely populated areas will probably have higher house price. Pretty good. So that's all for like the data visualization section. So what we'll look at next is try and see if there is correlation in our features and our labels. And if you haven't heard if you don't know what correlation is, it is sort of the the correlation coefficient is a number between -1 and +1 that indicates the presence or strength of any linear relationship between two variables, where -1 means highly negatively correlated and +1 means highly positively correlated, and 0 means there is no real linear relationship. And when I say linear relationship, what we mean is like if one variable increases, the other variable increases by a fixed amount. Um, in contrast to like exponential or other type of relationships where the increase is not constant. So we can get a correlation matrix of all the variables using the .corr function. So we'll do a housing. We can just continue using the same training data that we created before. .core. Let's run that. And that gives us a correlation matrix. So what that means is like this is the correlation between longitude and longitude, and it makes sense that it's 1. So you'll see that like all the diagonal values are always going to be 1. So this is not very useful because it doesn't really help us to know like the correlation between the features. What we want to know is the correlation between the features and the label. So the way we can do that is we can just get this column here, which is what we want. So we'll do median house value. And that will just give us this column. So now we can see which variables are more correlated to median house value. And you can see median income, as we sort of expected before, is highly correlated. What else? Thing, total number of rooms, a little bit, latitude, a little bit, not a lot. Maybe let's sort this so we can get a clear view. We can do sort values. This is a numpy series, so you can use this sort values function on any numpy series. And let's sort this in descending order so we can see the most correlated variables on the top. So what the way you do that is you do ascending equals to false. Let's run that. Okay. Again, this is obviously a variable will be correlated to itself. The next one is median income. Yeah, pretty much what we were talking about before. All right, so what we can do next is actually we could probably create another visualization like a scatter matrix, which is like our scatter plot of our variables. This is pretty important. So what I'll do is I'll import the scatter matrix function from pandas. I'll do from pandas.plotting import scatter matrix. And a scatter, what a scatter matrix essentially is it's just a combination of scatter plots of like all the variables. But because we have about 11 variables, we don't want a scatter plot with all of them because that'll be like 11 times 11 or like 121 scatter plots. So we can't fit that many scatter plots. So what I'll do is I'll just, because I sort of know from here that I want to look at the scatter plot between total rooms and median house value, median income and median house value. So I'll just pick those categories. So I'll do median house value, median income, and then total rooms. And then what I'll do next is I'm just going to copy this code off there. So I'll do a scatter matrix of these features, and I'll add a fixed size. Okay. All right. Okay, a few interesting ones. Maybe this. So we sort of expected this. So uh, if you see sort of like a linear pattern, it means that there is some correlation. The more it looks like a straight line, the stronger the correlation. So we can see that it has some kind of linear relationship, but not very strong. The other thing I wanted to show you guys is just because there are patterns in scatter plots does not always mean that there is like correlation. If you look at these uh, patterns, these are some scatter plots. You can clearly see that there is some relationship between the two variables, but all of their correlation coefficients are 0. That's because correlation coefficient only captures the linear relationship. So all of these look pretty much like a line. So that's why they are 1 and -1. So if the slope is positive, it's 1. The slope is negative, it's -1. All right, let's go back. All right, so that's pretty much our data exploration and visualization step. The next, we're sort of moving into the more interesting part of the workshop, which is like actually preparing our data for machine learning. And we will do this in 3 steps. Let's go back to this. Actually, yeah. So I'll come back to this in a bit, but what we're first going to do is we saw that there were some missing values in the total bedroom column. So we'll start with some data cleaning. And then what we'll do is we'll do some feature engineering. What feature engineering means is that you create new features using these existing features and maybe any domain knowledge you have. We also saw that there was one categorical column, and we said that we would encode that. So that's what we're going to do after that. We also saw that some of the features had really heavy tails. So we might standardize those and like get them to like a unit variance, like sort of like a normal distribution. Cool, let's go back. So we'll start with cleaning up our data. So we saw that there were about 200 missing rows in the total bedrooms column. And there are 3 ways we can fix these missing values. The first thing we can do is sort of like delete those rows. So the way you can do that is using the drop NA function. But before I do that, I'm just going to create another copy. Maybe I'll create a smaller data set. So I'll call it rows with NA or rows with nulls, which is going to be our, actually, before I do that, I'll create another copy of our data set. I'll call this housing prep, which we're going to use for our data preparation step. Housing.prep is equals to strat train set. Again, we are not looking at our test set. We are actually going to use the same data transformations for our test set as well, but we're just not looking at them at the moment, just so that we don't subconsciously bias our algorithm. So what I'm going to do is drop median house value. So what I'm doing now is I'm separating the features from the labels. So I'm dropping the label here to get just the features, and I'll explain why I'm doing that in a bit. And then I'll just get the label as well separately. So I'll do housing prep dot labels is equals to strat train set, and then just the median house value column. The reason, again, I am doing this is because when we do our scaling, our imputation for like missing values and all of that, we may not want to use the same transformation for both our features and labels. Yeah, so that's why I'm separating that. And now we're just going to do all of our feature engineering on just the labels. So let's get a smaller data set with some null values. The housing. Um, and what I'm doing here is I'm getting the rows that has null values. So you can do that using this is null command. And then I want any. So I want null values. I want rows that have null values in any column. And what so in any pandas data frame, there is two axes. Axis 0 is rows, axis 1 is column. So what I'm doing here is I'm saying, give me rows that have null values in any columns. And that's going to be a lot of null values like we saw before. So like 200 something, we don't need that much for this demonstration. So I'm just going to take like the first 5 from there. And let me just print that out here. And then, whoops, housing. Okay, I didn't run this cell. And then let me run that cell again. So we get the rows where total bedroom is missing. So the first way we can fix that is we can just drop all of these rows. So the way we can do that is, let's say, rows with NA, and then we can do a drop NA. Let's see what that does. Okay, so it just basically removed all the rows. And that's sort of like your last, yeah, that's sort of the last thing you do. Like if you can't do anything else, then you just drop those rows, but we have a few other options. So we'll try those first. The other thing you could do is just drop the column that has null values. This is also not something that's generally done, just because the column we are dropping might actually be like a significant predictor. So we want to keep as many features as possible. At this stage, we might drop features that are not useful later down the line. But for now, we want to keep as many features as possible, just because we don't know which ones are actually useful. So again, what I'm doing is, sorry, I forgot drop. So what I'm doing is I'm saying drop the total bedrooms column. Okay. Total bedrooms. What did I do? Oh, total bedrooms. I missed a S. Okay, so what that did is just drop that column completely. We don't want to do that either. What we actually want to do is impute these values, the missing values, from the rest. So when we're imputing, we can actually use a lot of different values for it. Well, something simple you could do is just replace all these nulls with zeros. But that's not really helpful. The other thing we could do is maybe replace it with like a central value, something like a mean or a median. So you take the median median total bedroom from all the other rows, and then just fill the nulls with the median value or the mean value. You can sort of decide on that based on your domain knowledge. But for this example, we will do median. So what I'll do first is I'll calculate the median, median housing rep. So total bedrooms, and then median. Cool. And then what I'm going to do next is I'll use the, let me just write the code first. So I'll say rows with NA, total bedrooms column. I want to fill NAs with my median. And then I can do a in place equals to true. What that does is just makes the changes in place. Um, then I can, let's print that out after uh, to see if that actually worked. Let's run that. Okay, so we see that all of the missing values has been replaced with 433. That's probably the median total bedroom. All right, so that was a bit time consuming. So if we had to do that for every column that had missing values, that would take a while. So we're going to make use of the imputer class from sklearn library. And so let me just uh, import that first. We're doing from sklearn import simple imputer. And then I'm just going to instantiate a simple imputer. And you'll, so the syntax for a lot of these sklearn transformers, you'll see is the same. So what you do is you import the class first, you instantiate it, and then I'll get to that in a bit. But what you do is you fit that to your data and then you transform your data. So I'm instantiating an imputer using the strategy median. So let's run that. The other thing we might want to do before we actually impute is separate our numerical columns, because you can't impute categorical columns with the median. So what I'll do is I'll get the numerical columns and I'll just call it housing num is housing rep. Then I'll select this function from pandas called select d types, and I want to include the NP number class, which is a data type from NumPy. Again, the syntax here is not important. Yeah, if you understand the steps, that's pretty good. So I'm getting the numerical columns because I only want to impute those. Let's see if we actually got it right. We can do housing num.head. Cool. It looks like it dropped the categorical column. Okay, so now let's fit our imputer. So by fitting our imputer, what we're doing is just calculating the median for all the columns. So I'll call imputer.fit to our dataset. Our dataset is housing.num. Yeah, so okay, so it fitted this imputer to our housing num. So what that did is, let me show you. So if I do imputer.statistics, let's run that. So essentially what it did is calculated the median for every column. So the median for longitude is this, the median for latitude is that, and so on. So now what we need to do is use this imputer to transform our data set. So the way you do that is, actually, I'm gonna create a new data set here. Just because I don't want, I might make some more changes to this numerical column. So for just demonstration, I'll do x equals to imputer dot transform, and then I'll pass in our data set housing num. And then let's take this, let's print that out. Okay, so this gave us a NumPy array, not a data frame, which is hard to use. So I will convert that back to a NumPy array. We'll do that is I'll say housing num is equals to bd.dataframe. So we can just use the data frame function from pandas to convert a NumPy array to data frame. And data frames look like formatted like this. It has column names, it has indexes, but NumPy arrays are sort of like just nested lists, which are harder to deal with. So I'll I'm trying to convert X. And I'll just take the column names from our original data set. So column names equals to housing underscore num dot columns. And we also need the indexes, just because we used when we created our test set, we randomized these indexes. So we need these indexes to know which of these rows actually belong to our training set and test set. So I'll do housing dot num dot index. So that should work. Yeah, so we get back our original data set with the total bedrooms imputed. All right. Okay, so the next thing we are going to do is encode our categorical variables. We just have one categorical variable, which is this ocean proximity here. And again, there are two ways we could encode this into a numeric variable. What we could do is we could do like an ordinal encoding. What that does is, because there are 5 categories, 1, 2, 3, 4, 5, it'll just give them a number between 1 to 5. So let's say this will be 0, this will be 1, this will be 2, this will be 3, this will be 4 and 5. Let's try and do that. But I'll tell you why that is not a good idea in this situation. So let's get the categorical column first. So I'll do housing cat equals to housing prep. And again, I'm just using the same preparation set that we created as a copy of our training set. Ocean proximity. Let's see. Okay, so another thing you might have seen here is I want to keep it. So I'll show you what happens if I do single brackets. If I do single brackets when getting a column, it just gives me a NumPy array. So instead of that, I actually just want to keep it as a data frame. So what you can do is add another layer of brackets here. And then that gives you a data frame that just has one column. Okay, that's much better. Okay, so we're going to use another transformer from the sklearn library. So we'll do from sklearn dot pre-processing import ordinal encoder, and then we'll instantiate that. So the pattern is the same for like all of this transformation. We import a class and then we instantiate that class, and then we will fit and then we will transform. But I'll show you something else in this case. So most of these transformers actually have another function, another method called fit transform. And if you use that method, you can basically achieve both fitting and transformation in the same step. So I'll do housecat encoded is this ordinal encoder. Instead of doing fit first, we'll do fit underscore transform. So we'll fit our original data set and transform it at the same time. We'll do housing cat. Let's do that. Okay, let's see what we got. Housing cat encoded. Okay, so yeah, basically inland was given the value 1, near ocean 4, again, inland 1. Yeah, so it gave it values between 0 to 4. But the problem here is that ocean proximity does not have any inherent ordering. Like 0 is not better than 4, or 4 is not better than 0, or in that order. So we're going to use a different kind of encoding. called one-hot encoding. If you've taken like a introductory data science class, you might have heard this. So what we do is we create dummy variables for each of these classes. So essentially, we're going to add 5 more columns to our data set because there is 5 categories here. And for every row, like if it was inland, the inland column will have 1 and every other column will have 0. Let's do that. So again, we will import another transformer from the sklearn library. So we'll do sklearn preprocessing, import one hot encoder. Let's instantiate that. We'll do cat encoder equals to one hot encoder. And I'm just going to put this in for now, and I'll explain in a bit why I did this. So sparse equals to false. So let's run that sklearn dot, maybe it should be pre-processing, yeah. Okay, that worked. So let's do the same thing again. So I'll do housing cat one hot encoded is equals to our one hot encoder dot fit transform. So achieve fitting and transformation in the same step. And then our original data set, which was housing cat, only the category code column. Okay, and then let's print this. Whoops. What did I miss? Fit transform. It did pass. Okay, let's see what's up. Missing one positional argument. X equals to. Interesting. Oh, sorry. I'm using the class, not the instance I created. Okay, so yeah. Okay, so let's look at our original data set. So actually, I'm just gonna do something else first before we look at that. So I'll do our cat encoder, then cat categories, just so we can see the categories that we have transformed. So the first column here is less than 1 hour from the ocean. The second column is inland. So our first value here was inland. So the second column is 0 for the first row, and everything else is sorry, it's 1 and everything else is 0. So going back to this, okay, this sparse here. So if I didn't do this by default, sparse is true. What that does is it gives me a sparse data set. So sklearn, what sklearn does is a sparse data set means if you had a lot of categories, imagine like, let's say 100 categories, this would be a 100 by 100 matrix, which would take up a lot of space. So instead of giving you a 100 by 100 matrix, it just gives you the position of the 1 in each row instead of adding these zeros, because those are like, we know that if 1 is in the second column, the rest of them must be 0 because it's like either or, it can't be more than 1. But the reason we didn't do sparse in this case is just because we have 5 categories, and that's a little bit harder to understand. Okay, so that's all for our data cleaning and encoding. So the next thing we're going to look at is feature engineering. So feature engineering is we use our domain knowledge and maybe create new features from our existing features. So going back to our correlation matrix, so we saw here that these two, well, it was like total rooms. Total rooms in and of itself is not very useful. What might be more related to median house value is the number of rooms in each household, right? So we can get that by dividing total rooms by the number of households in each district. Same for total bedrooms. So it's not really informative knowing the total number of bedrooms in a district. What might be a better feature is, let's say, um, the ratio of bedrooms to rooms in a house. So how many bedrooms there are for every room. So you can get that by dividing total bedrooms by total rooms. Again, maybe things like population is also not very useful. We could do population per household, or maybe not. Maybe let's try engineering those features and see if the correlation increases. Okay, so I'm just going to copy some code again. So I'm doing housing prep. I'm creating a new column called rooms per household, which is going to be total rooms divided by number of household. And then I'll add another column called bedrooms per room, which is total bedrooms divided by total rooms. And finally, one last column, population per household, which is total population in a district divided by the total number of households. All right, so let's do that. So now let's see what if we have any new variables that are correlated. So I'm just gonna paste this code. So what I'm doing here is I separated the labels and the prep and the features earlier. So I'm just gonna merge them again. And then I'll get the correlation matrix and sort it. Cool. So median income is still the top, but we can see that total rooms, so this variable here, rooms per household, does actually a little bit better than total rooms. Population per household, that was probably not a good decision. That doesn't really help us. This one worked pretty well, bedrooms per room. It is negatively correlated, which is also good. Like we want correlation in any direction. It's only the magnitude that matters. The sign doesn't matter. Okay, pretty good. So the last thing we will do before feeding this data to our machine learning model is scale them. So we saw here that some of the features are heavy-tailed, and we could scale our data, scale these features in two ways. We could use something called min-max scaling. What that does is it basically takes the value, subtracts the minimum, and then divides by the difference of the maximum and the minimum. That's not very important to know, but basically what does is it squashes all the values between 0 and 1. But this process is a little bit sensitive to outliers, as you can imagine, like because we are using max and min. So if the max is like really, really high, like if you have a value that's really high, then it will squash the values really tight. So we don't want that. A better way for us would be just to something called like z-scaling or like standardizing. You might have done that before. So what you do there is you take the value, you subtract the mean, and then you divide by the standard deviation. What that gives you is like a unit, a zero mean and a unit variance. So this will sort of now then look more like a normal distribution, which is better for our machine learning model. All right, so we're running short on time, so some more copy paste needed. Cool. So first thing I'm going to do is, again, import this transformer called standard scalar. And then I'm going to instantiate a standard scalar, and then same as before, I'm just going to fit and transform. The other thing to note here is that I'm only transforming the numerical columns that we separated before, because you cannot standardize the categorical column. Cool. Again, this is also giving us a NumPy array, but this we'll just keep for now. It's not too big of a headache. We could transfer it back to a data frame, but that's not necessary at this point. So the next thing, what I'm gonna do is, so actually let's go back and like inspect what we did so far. So we separated our features and labels, and then we did some feature engineering. We created some new features, which was where? Yeah, we created some new features. We imputed the missing values here, and then we encoded our categorical variables, and also scaled our numerical variables. So this is a lot of steps. So imagine you have new data every time and you have to retrain your model after you've pushed it to production. You don't want to do all of these steps like manually every time. So what we do is we create something called a data pipeline. So sklearn actually has a custom class called custom transformers, which you can use to build a class that will do all of these steps one after the other in the right order. But that's actually a little bit too complicated for this workshop. So what I've gone ahead and done is I've just created a function which we can just copy. Let's see, where is that? So you'll see that the function is nothing that we haven't seen before. Sorry. Yeah. So essentially, this function here, this data pipeline, is I've copied over all of the code from before and then just put it all in a function that we can reuse anytime we want. All right, so let's paste that in. So this function will give us our output labels and features. So now let's run our training data and test data through this pipeline so that we can get them all clean, feature engineered, and scaled. So I pass the training set, and then I'm getting back the training features, the training labels, and a column with the feature names, not too important in this case. So that's good. And then I also want to do the same for our test data set. But I'm still not going to look at the test data set. I'm just going to pass it into our data pipeline. Cool. So we have test features, training labels, test labels. All right. So now we're ready to move on to our machine learning model. So the first machine learning model we're going to look at is a linear regression model. You've probably come across it in maybe year 12 or like first year stats. So let me copy that over. So what I'm doing is it's pretty much the same as we've done before. So from sklearn.linear model, I'm importing this model called linear regression. I am instantiating that. Then I'm fitting it on my training data and my training labels. So labels are, again, what we're predicting, and data are like these. This is the feature that we are using to predict. So again, I'm still using my training data to train my model. That was pretty fast, but some of the other algorithms we might use might take a while. So what I'm gonna do next is I will try and actually, before I even test it on our prediction set, I'll try it on some of my training set, and I'll explain why that I'm doing that in a bit. So I'm just getting some data and some labels from my train set. And then I'm going to predict. So what I'm doing is some predictions is linear regression, which is the model we created here. Dot predict some data, which is our features. Do that. Let's print out our predictions. Those are predictions. Let's see what actually our labels were. Okay, 82,000. The actual was 72,000. This was 330. Yeah, and then this is 279,000. That's a very big gap. So this is not a really good model, but that's fine. So what I might also do is like just check the difference between the predictions and our original labels. A difference of 10,000, difference of 52,000, difference of 73,000. So this is clearly not a very good model. But instead, so I just tried it on like five data points from my training set. What I'll do is I'll actually get the score on the entire training set and see how it does. And the metric I'm going to use is called root mean square. So I'm just going to import that. sklearn.metrics, import mean squared error. So these metrics, it's not important to understand them now, but you can just imagine that they are, they give you a measure of error, so the lower the better. So what I'm doing is I'm predicting on the entire training data set. Again, why am I not predicting on the training data set just yet? It's because I actually want to know first if I'm overfitting or underfitting before I actually try it on my test set. So let's see this. So it's telling me that on an average, oh, actually, this is just the mean square error. I actually need to square root that before I. So I'm using the np.square root function from NumPy to get a square root of this error metric. So on an average, I'm about $67,475 off, which is again not pretty good, given that like most of the houses were around the 150,000. So if you're 67,000 off, that's very bad. So we can improve this model in a lot of different ways. We could either first select a more powerful model, maybe tune up our features a little bit, give it some more informative features, or remove some of the constraints on this model, which is like hyperparameter tuning, which we will get to in a bit. I don't know if we'll have time to do that, but before we do all of those, we'll try like a more complex model. So the next model we'll try is, I'll actually skip the decision tree regressor and go straight to this model called random forest regressor. So let's try that first. All right. So again, I'm importing random forest regressor from sklearn.ensemble. So random forest regressor is actually an ensemble model, which means that it is a collection of a lot of models. In this case, a random forest model is a collection of a lot of decision tree models. Not super important to understand what those terms mean now. But yeah, just understand that we tried a simple model first. Now we are training a more complex model. And n estimators is like a parameter that we're giving it. So that's the number of decision trees that we're using. This will take a while. While that's happening, we'll just write the code that we will use to check the error. So to check the error, I'm actually going to use a different method. So we saw, before I get to that, so we saw here, okay, so it's done testing. So let's look at its error. Decision tree regressor. Okay, just gonna copy the code from there. Oops, not this. All right, so I'll explain what this code is doing in a bit. But let's run this first. Okay. Mhm. I forgot to import this. Okay. This is also going to take a while to learn. So we're actually using a different way to measure the error here. This is known as cross-validation. And what we essentially do in cross-validation is instead of going to our test data, instead of using our test data to check this, to check the error, what we do is we test it on our training data by creating folds or partitions of our training data. So in this case, we're dividing our training data into 5 parts. And when we run it for the first time, we train it on these 5 parts of the training data and then test it on this. Again, we train it on these 4 parts and test it on this. So we essentially, we do 5 iterations of this where we use one portion of the training data to test it every time. The reason we do that is because this gives us a much better metric of error. And we only want to reserve our test set when we are absolutely certain that this is the model we're going to be using. But we haven't reached that stage yet, just because we have another stage called hyperparameter tuning. But I think I'm running a little bit over time. So we'll see what we can, we might go on for like 10 or 15 more minutes. But actually, I'll just run through the code so that we finish in time. Okay. So what we are doing is, so we check the cross-validation error for this random forest regressor, and that gives us a cross-validation error of 50,000. So this is much better than the linear regression model that we used before. So we could have actually skipped to the hyperparameter tuning stage for our linear regression model, but instead of doing that, we tried a more complex model first, so that it was better. Now we are going to tune our hyperparameters. So what hyperparameters are is they are parameters that your model cannot learn from the data itself. These are parameters that you have to sort of feed into the model by doing, let's say, like some sort of brute force search. Hyperparameters dictate how fast or slow your model learns, and they can vary your performance by a lot. So okay, let's go back to this. So what we're doing now is we're doing a grid search for hyperparameters. So when we trained our random forest for the first time, you saw that we gave this parameter n estimator is 100. That's just arbitrary number, some arbitrary number that I used. But what we're doing in this stage is actually getting what is the best parameter to use for our model. So what it does is it tries a combination of hyperparameters. It does a grid search. So it'll try every combination of 3, 10, 30, and these max features. And then it gives us which is actually the parameter that we should use. So in this case, it tells us that you should use max features as 6, net n estimators as 30, not 100, which we used before. Yeah, and random state is just that. So you can see that when it looks for the parameters, the score goes up, down, up, down. And you can see that when it actually came to this one here, max feature 6 and estimate as 30, which is this, the error was the smallest. So it essentially did like a brute force search. But if you have a lot of parameters, this grid search might take a long time. So there's another process called a randomized search, which just looks for parameters randomly. And this is, in practice, it gets to the correct answer much faster than like a brute force. All right, so at the end, what we can do is we check, based on our model learn, what features were actually important. So we saw that, just as we predicted, median house income was the most important predictor. Inland, whether or not the house is close to the ocean or in the inland, is also a pretty good predictor. Location, median age, number of bedrooms, all of those are pretty good predictors. So once you have settled on your final model, what you can do is then test your model on the test set. And basically, in our case, it was the random forest model, which we got from the grid search. And it gave us a final score of 64,000 on the test set. So it's important to make this distinction that the model actually performed much better in the training set, which was like 50,000 something or like 49,000 something. But that's actually not a good indication of how it will perform on unseen data, which is what we did here using our test set. So you always have to use your test set and the end to get that measure. So once you have that, you don't want to retrain your model every time. What you can then do is save your model and then upload it. And let's say like use something like Flask or Streamlit to create like a REST API that you can connect to your front end to pass data to that model, and then the model will just give a prediction. So the way you can save a model is using this library called Pickle. So we are using our final model as this file, which has a .pkl extension. And you can then load your model anytime you want to test it again using this load model function. And when we try that, it gives back our original model. All right, so near the end. So after you have your final model, what you will do is you'll deploy your model. As I was saying, you could use something like Flask to create a REST API for your model. If you're building like a model for developers only, you don't probably need to build a front end. Like they can just send queries to your REST API and get predictions. But if you're, let's say, building like a customer facing product, so a website maybe that gives house price predictions, then you will build a front end and connect it to your model's REST API so that maybe the users will have some input fields, the users can enter the features and they'll get predictions. You also want to collect fresh data regularly because your model will change performance if the data changes. So let's say like if you have data about COVID, your model might start become become significantly worse. So you need to collect fresh data regularly. And then we already have that function that does your data pipeline. You can also write a function to train and fine tune your model in regular intervals. And then you can use cron jobs on Azure or any other cloud platform to basically automate these model training. And finally, you can also write another script that will evaluate your old model. And when you have retrained, it will evaluate your old model and new model based on the updated test set. And if your model hasn't decreased in performance, it will push the new model to production. But if you see that with new data, your model starts to perform badly, you will again come back to this stage where we go through all the data exploration, data feature engineering, and everything to figure out why your model is performing well, not good. All right, that was all. Thank you everyone for coming. We'll finish it there. Thanks for sticking to the end. That was very long.